Welcome back everyone to section number 9. Again, this is linear approximation and differentials. In this video, our goal is to do just a few more examples, right? And actually utilize, again, tangent lines are really the heart of these things, and to solve a few problems relating to linear approximation and differentials. So, let's get to it. This first example, we have the function sine of x is under consideration. And we want to find the linearization of the function at pi over 4. Okay, well we can use our linearization equation, which says L of x is equal to f of a plus f prime of a times x minus a. But again, remember, this isn't a new thing. This is just our tangent line. So you really don't even have to memorize this thing, so long as you already know the equation for a tangent line. So in this case, well, again, our function is sine of x, and our point A is pi over 4, so we can go ahead and start maybe solving for some of these things. So if I wanted f of a, well, that's going to be sine, that's our function, of pi over 4. And thinking about my unit circle, we'll get root 2 over 2. All right, for f prime of a, well, let me go ahead and first of all take the derivative of my function. So the derivative of sine is cosine. And then f prime of a, again, my a is pi over 4. Well, I'll just plug in a pi over 4 everywhere I see an x. And that will give me, again, root 2 over 2. How boring, right? And of course, a I already know. So let's go ahead and assemble these pieces. And we get L of x is equal to, well, f of a, that's root 2 over 2, plus f prime of a, that was also root 2 over 2, times x minus a, so x minus pi over 4. And again, well, this is my final answer, but I want to emphasize that the linearization is just the tangent line. So I went ahead and I graphed my function sine of x. Again, we were at this point, pi over 4, and I graphed our answer, the linearization, root 2 over 2 plus root 2 over 2 times x minus pi over 4. And you can see that, again, this is just the tangent line. Okay, next up, I would like to use the linearization to approximate sine of 11 pi over 40. And the claim is, right, 11 pi over 40 is close to 10 pi over 40. Well, and that's the same thing as pi over 4. So again, this value right here, 11 pi over 40, is close to pi over 4, this thing that we're pinning our tangent line to. Again, we were pinning it here at pi over 4. And so we have this nice statement from our previous video way up here, right, that the function's height and the linearization, or the tangent line's height, are approximately equal to each other as long as x is close to a. And in this case, the value 11 pi over 40 is indeed close to pi over 4. So the linearization will do a good job approximating the function, right? So this is our function, sine, at 11 pi over 40. So again, what we're using here is f of 11 pi over 40 will be approximately equal to the tangent line's height at 11 pi over 40. Well, here is my tangent line equation, or my linear approximation. Let's go ahead and plug in 11 pi over 40 everywhere I see x. So L of 11 pi over 40 is going to be equal to root 2 over 2 plus root 2 over 2 times, and again, everywhere I see an x, I'm going to put 11 pi over 40. And maybe instead of pi over 4, let me go ahead and write this as 10 pi over 40. Oops, that's a horrible 40. There we go. And we can do a little bit of simplifying. So this is going to be root 2 over 2 plus root 2 over 2 times an 11 pi over 40 minus 10 pi over 40. That's going to be 1 pi over 40. And we could simplify a little bit more beyond that, but that's probably where I would end. And so again, let's check the graph to see what we actually did here. We used the linearization, and notice that I've graphed 2 points here. 1 point's on the red line and 1 point's on the blue line. and we're interested in what's happening here at 11 pi over 40. We would like to know the function's height at 11 pi over 40, but the claim is sine's tricky, right? And so lines are a lot less tricky. And so we can see that the height of this red point and the height of the blue point, right, they're very, very close to each other, right? These points are very, very close to one another. And so we use the tangent line here to approximate the height of sine at 11 pi over 40. And so you can see they're actually very, very close to one another. The linearization does a good job. All right, moving on to our next example, we have use linear approximation to estimate the cube root of 1001. And now notice that this is a little bit more difficult of a problem because we don't have a function, right? So the question is, what is our function that we want? And then it also did not specify an a value, right? Where should we actually pin this tangent line to? And so the claim is this is actually pretty similar to if we had just been given b up here, right? So use linearization to approximate sine of 11 pi over 40. So we can see here that our function was sine, so that's kind of the function that's in question. And then 11 pi over 40, well, this is close to some sine value that we actually know, right? We know the sine of pi over 4. So this is a value that's close to this x value. So using those two ideas, I would like you to pause the video and try to get as far as you can for this example, right? So again, you're going to need to figure out what is your function and what is your a value in order to solve this problem. So go ahead, pause it, try to get as far as you can. Go for it. All right, so let me move us forward a little bit and let's just verify that we have the same things. So the main function that's being applied here is that we have the cube root function. So in this case, our function's value is going to be the cube root of x. And our a value should be some point that's near 1001 that we know the cube root of. Right? So 1001, we don't know the cube root of this without a calculator. But the claim is at 1000, well, we actually do know that, right? So if I use my a value is 1000, then the function's value at 1000, right? The cube root of 1000 is equal to a nice even 10, right? Because this has 3 zeros, and so you take the cube root, and that just gets you down to 1 0, just like the square root of 100 is 10, right? Okay, so this should be our function and our a value. Now with these, see if you can finish it out. All right, so this is how far I got, but I want to talk through a few things and make sure we're all on the same page. The first thing here is, right, the cube root of x is the same thing as x to the 1/3 power. So when I go ahead and I take the derivative, right, that 1/3 is going to come down and I'm going to get x to the negative 2/3. Now x to the negative 2/3, we can go ahead and push that into the denominator and make that exponent positive, right? So I'm going to have 1 over x to the 2/3 power. Now I need f prime of a. Remember my a value is 1000. So when I plug in 1000 to this, I'm going to need to be able to evaluate 1000 to the 2/3 power. Again, I don't have my calculator, right? Well, luckily with 1000 to the 2/3 power, notice that you have raising to the second power and raising to the 1/3 power. And the claim is that you can do these in any order that you'd like. So when I see 1000 raised to the 2/3 power, I say, okay, well, let's apply the 1/3 power first, right? So 1000 to the 1/3 power, we already know from back up here, it's the cube root of 1000, and that's 10. So that's going to be 10, but then I also have to square it, right? Because it's raised to the 2/3 power. So we have 10, and then I square that, and that gives me 100. All right, so we have the 1/3 times 1/100th, and that's going to be 1/300th. So that gives us a linearization of f of a. So that's the function's value at 1000, which was 10, plus f prime of a. We solve that as 1/300th, and then times x minus a. Again, my a value was 1000. So this is the linearization, but we would like to approximate the cube root of 1001. So remember the cube root of 1001, well, that's going to be the function's value, right? The function is the cube root at 1001, and the claim is the function's value at 1001 is approximated fairly well by the linearization at 1001. Again, because 1000 and 1001 are close to each other, right? X is close to A. So I would like to figure out the linearization at 1001, and the claim is this will be a good approximation. So L of 1001 is going to equal, well, everywhere I see an X down here, I'm going to plug in 1001. So I have 10 plus 1/300th times 1001 minus 1000. So that's just going to be 1. So this is going to be 10 plus 1/300. And that is my final answer. This is the linear approximation for the cube root of 1001. All right, we are 2 problems down. Let's try another one. We've been sticking with linearization, but the claim is we also have to think about differentials, right? So here's my curve y equals cosine of pi x, and I would like to be able to, first of all, find the differential dy for this curve up here. And so remember, our differential dy was equal to this whole f prime, and if we're just leaving it in terms of a formula here, this is going to be f prime of x times dx. And then remember, we're going to plug in a here later on when we actually start evaluating stuff. So the differential, well, we can calculate out the derivative of this, right? So if here's my function, f prime of x is going to be equal to the derivative of cosine is negative sine. Leave the inside alone, then multiply by the derivative of the inside, right? I have to use the chain rule here. And so I get dy is equal to f, let me go ahead and substitute that in, right? Here's my f prime of x, so this is going to be negative pi sine of pi x times dx. All right, so that is the differential, and remember, these are actually used to calculate or to approximate the change in the function's height as you move x values. So, okay, imagine that we start at 1/3 and we move 2/100ths to the left, right? So negative 2/100ths. The question is, how much did the y value change, right? Calculate out this dy. Well, let's go ahead and plug it in. Dy is equal to negative pi times sine of pi x. Well, this is going to be our 1/3. And then times dx. So if I move 2/100ths to the left. All right. So let's see, negative pi, and now sine of pi over 3, right? So sine of pi over 3, that's going to be my root 3 over 2. Got ahead of myself there. Root 3 over 2. And let me go ahead and express this as negative 2/100ths. We can see that there's a little bit of cancellation. These 2's cancel out. We have a couple negative signs that nicely cancel out. And so I would leave my answer as pi root 3 over 100. So this is saying that the function changed approximately this much, right? So pi times root 3 over 100. Not a very beautiful answer, but we could plug this into our calculator and get a nice decimal approximation. All right, one last one on differentials. Use a differential to approximate how much the y value, right, y equals root x squared plus 8, changes as x moves from 1 to 1.02. So in this case, this doesn't give me a dx value, right? So we need to do, this is where it ends at 1.02, and it started at 1. So how much did it change? Well, it changed in this case 2/100ths, but it went in the positive direction. So a little bit different than the last one. Here we went in the negative direction, so we ended at a value smaller than 1/3. Here we ended at a value greater than 1, right? So we went in the positive direction. So there's our dx value. Let's go ahead and calculate out dy, and dy is going to be f prime of x times dx. Luckily, I just figured out what my dx is. Let's go ahead and calculate out the derivative of this function then. So f prime of x is going to be, well, remember that this is the same thing as x squared plus 8 raised to the 1/2 power, right? Square roots are the same thing as being raised to the 1/2 power. So when I take the derivative, I'm going to have the 1/2 comes down, leave the inside alone, reduce my power by 1. then we multiply by the derivative of the inside, right? Thanks to the chain rule here. A little bit of cancellation with the 2's. And I can go ahead and write, let's see, well, with this negative exponent, this is going to be in the denominator. So I'm going to have an x squared plus 8, and this is raised to the 1/2 power. So it's going to have a square root. And then in the numerator, what's left? Well, it looks like just an x. Okay, let's go ahead and plug in our specific a value. So in this case, it's a nice even 1. So when I plug in 1, so f prime of 1 is equal to 1 over the square root of 1 squared plus 8. So that's going to be 1 plus 8 is 9. So this is going to be 1/3. So here's the derivative at this nice value, this nice a value, where we started. So in this case, we have dy is equal to, well, f prime of our a value, 1. So that's 1/3 times 2/100ths. So 2/100ths. And so in this case, well, this actually simplifies down to 1/50th. So 1/3 times 1/50th. So that's going to be 1/150th. So the claim is the y value didn't change a whole lot, right? Just 1 over 150. That's approximately how much this y value changes as x moves from 1 to 1.02. All right, guys, that is it for this video, and that's it for Chapter 2. I'll see you guys next time in the wonderful world of Chapter 3.